Hello everyone and welcome to this lecture. In this lecture we will start a very interesting discussion. The discussion is on what eigenvalues can tell about the graphs. We have already seen many beautiful properties of graph that we can infer from the eigenvalues. For example, if you take adjacency matrix, it can tell how many number of edges graph has, okay, how many walks of certain length or how many closed walk of certain lengths are there, right? We can infer from the eigenvalue of the adjacent. Similarly, whether graph is bipartite or not, okay, and there are many more, okay. Similarly, if you look at the Laplacian matrix, right, we can tell whether the graph is connected or not just by looking at the eigenvalues, okay. Then we take signless Laplacian matrix, okay, it was again telling you whether the graph is bipartite or not just by looking at its rank. If rank is n minus 1, then the graph is bipartite, otherwise otherwise non-bipartite, right, when the rank is n, okay. And by the way, there is a very nice connection between rank and eigenvalues when the rank of a symmetric matrix is nothing but number of non-zero eigenvalues, okay. But now the interesting question is this, okay, can eigenvalues tell everything about the graph? Okay, are they kind of fingerprints of graph? So like when we put fingerprint, it can determine us, okay. So I mean, oh, it is this person whose fingerprints are there, right? Can eigenvalues be treated as fingerprints? Okay. Till 1957 it was believed that yes indeed, by looking at the eigenvalues, basically it tells that eigenvalues can uniquely determine the graphs. But then mathematicians are mathematicians, they come up with a counter example, and this counter example is this, okay. So this graph, yes, this one, and these two graphs have the same eigenvalues. Let me tell what they are. So this is nothing but k14. So eigenvalues, we have already seen that eigenvalues of basically complete bipartite graph. So this is nothing but 2 minus 2 then 0 0 0, okay. And then similarly the eigenvalues of this are, you can actually verify that these eigenvalues are this, okay. By the way, this pair was given by Collage and Sinogovich in 1957, and this is also known as Saltaire pair. The reason is because if you merge, or I mean superimpose these two graphs, this looks like flag of Scotland, okay. Very good, very good. So yeah, now I mean this was about the adjacency matrix, okay. Similarly, with respect to the other matrices like Laplacian matrix, signless Laplacian matrix, and many more, right, can can we have two different graphs but have the same eigenvalues? Like you see that these are two different graphs. Now let me put more formally what I mean by different. Different here means non-isomorphic. Non-isomorphic means the structural or topology of two graphs are different. For example, if you see here, there is a cycle on the left hand side, right, but there is no, this is a tree, I mean right hand side one is tree. So maybe you all of you know what I by meaning of what we mean by isomorphic, okay. So let me formally define it, okay. So isomorphic, okay, graphs, very good. So isomorphic graphs are two graphs, let me call G1 and its vertex set is V1, E1 and G2, and suppose its vertex set is is V2 E2, okay, V2 E2, okay. Then G1 G2 are called isomorphic, then G1 and G2 are called isomorphic if basically we can relabel the vertices of these two graphs and we have the same structure, okay. These are called isomorphic if there exists a function, in fact a bijective function, okay, a bijective function which is nothing but 1 1 on 2 function f from vertex 1 to vertex 2, and there is one more condition, and the edge ij which is in E1 if and only if this, if you basically after the renaming or after basically the function, okay, whatever the value of this fi and fj is, they must also have edge between them in E2. Okay, so this is if and only. So very simple. You just let us see one example of it, and please verify that these graphs are indeed isomorphic. So maybe this one, yeah, okay, so let me, okay, very good. So these two graphs, you could just cook one onto function, bijective function, and prove that these two graphs are actually isomorphic graphs. Very good. Now let us come back to our interesting question again. So we have seen that two graphs may be non-isomorphic, but they may have the same spectra. Okay, so such graphs we will call cospectral graphs. Okay, cospectral graphs. Okay, so graphs which are isomorphic, sorry, non-isomorphic, graphs which are non-isomorphic and having same spectrum. Okay, spectra. Very good. Okay, so these are called basically co-spectral graphs. So for example here, this graph, this is a pair of graphs. Again let me draw it. Okay, is co-spectral graph with respect to it's a I mean correct sentence is so these G1 and G2 are co-spectral with respect to adjacency matrix. Okay, adjacency matrix. Very good. Okay, and by the way, there is no graph, no such pair on less than or equal to 4 vertices. Okay, so this is actually the smallest pair, smallest size pair you may say in terms of vertices. Okay, of a co-spectral graph. Very good. Now let us see some graphs which may be co-spectral with respect to some matrix, okay, but may not be co-spectral with respect to other matrix. It just you please verify. Let me give you one example which you have to verify. So suppose if I take this graph, okay, and this one, and this graph. If I hopefully I am doing it correctly, okay, you just check that this graph, these two graphs are actually I would say are co-spectral with respect to L but not A. They are with respect to co-spectral with respect to L, the Laplacian matrix, but not the adjacency matrix. I mean you just verify that the Laplacian matrix of basically these two guys are the same eigenvalues. Okay, but I mean it is easy to see why this eigenvalue of these two graphs will be different for adjacency matrix. The reason is, I mean, one graph is non-bipartite graph, other is bipartite graph. Okay, and we have already seen that bipartite graphs have basically what the eigenvalues are symmetric, right? And this is if and only if condition, okay? But for non-bipartite graph this is not the case, right? So here you see that the eigenvalues must be different, okay? And you just check for the Laplacian case, indeed the eigenvalues are coming out to be same. Okay, very good. So now what? Okay, oh, by the way I missed one thing. Okay, see, when I was telling about this isomorphism, okay, let me tell you, this isomorphism problem is again, I mean, for if you talk about mathematics and theoretical computer science, okay, another interesting problem. It is interesting in the sense that it is still not decided whether it's a very difficult problem or it's an easy problem. By difficult problem, we have already given some example of very difficult problem, like finding the clique number, finding the independence number, what is the chromatic number of graphs. There is no polynomial time algorithm for such, and it is proven that there cannot be polynomial time algorithm unless until the famous conjecture P equal to NP happens, right? But for this problem, whether two graphs are isomorphic or not, okay, there is no polynomial time algorithm, but it is still not proven that there cannot be a polynomial time algorithm unless P equal to NP. So this is a kind of a very typical interesting class of graphs, okay? And the question is, can eigenvalues help us? Can eigenvalues help us determining whether these two graphs are isomorphic? But we have already seen no, right? Okay, so, and in fact it's quite intuitive also, right? If eigenvalues can solve, then it is likely that these can be solved in polynomial time, because in most cases we can do so, right? We can, eigenvalues are, even though they are roots of characteristic polynomial, it's very, and it's theoretical, it is not possible. But yeah, in general there are many good algorithms, okay? So there is a lot and lots of hope that if this was true, that if eigenvalues could have uniquely determined the graph, maybe these eigenvalues could have helped in giving very good insight into graph isomorphism, okay? But unfortunately this is not the case. But yes, there will be class of graphs, in fact very large class of graphs, for which eigenvalues can indeed determine, oh, these graphs are uniquely determined by the eigenvalues, okay? Very good. So with this, let us move the discussion ahead, okay? Now we have seen some graphs may be cospectral with respect to certain matrix, eigenvalues of certain matrix, but not with respect to other, okay, like here. And let me tell you one more interesting example. So let us take this graph, okay? Let us take maybe this graph. So this is G1, and then take maybe this graph, okay? Both of these graphs has 4 vertices, okay? I will tell you that definitely these graphs are not cospectral with L, not cospectral with L, and in fact A also, right? Because right hand side is a bipartite graph, left hand side is non-bi, so L and A, okay? But cospectral with respect to I would say with respect here, with respect to L, with respect to signless Laplacian matrix, okay? Signless Laplacian matrix, I will tell you, maybe we have already seen what this matrix is, signless Laplacian matrix, okay? Remember, we have seen Laplacian matrix. So Laplacian matrix was what? Incidence matrix times its transpose, Q into Q transpose. We could actually write this as degree minus adjacency matrix, degree matrix. There is something called signless Laplacian, and the introduction of this is we have already seen. Remember, we have seen 0 1 incidence matrix, right? 0 1 incident matrix is nothing but incidence matrix where wherever there were -1 you put there +1, right? And this was another beautiful matrix which was telling that if the rank of this matrix is n-1, then the graph is bipartite, otherwise graph was non-bipartite. And this, suppose I denote it by QS, so sinuous Laplacian is given by this matrix, and this is nothing but, it's easy to verify this is right. Okay, very good. But why these two graphs are co-spectral with mod L, okay, but not with L or A, okay? Remember that, okay, so there is one thing that if you see the eigenvalues of okay, no, yeah, this is correct. So if I tell this that suppose if you do this exercise, okay, so maybe I will take some another matrix, okay, some another matrix, so that matrix is nothing but this QS times transpose times QS, okay, QS times what will be this matrix? Suppose the number of vertices so are n is suppose vertices and m is suppose edges, number of edges, okay. What will be this matrix? Remember, this matrix is what? N cross n. This matrix is m cross m. So this is m cross m, h times m, okay. Now I am telling you this matrix is nothing but this matrix is nothing but 2 times what we call Im plus some matrix, and this matrix B is very interesting one, okay. This matrix is actually line graph of adjacency matrix of adjacency matrix of, let me tell right clearly, adjacency matrix of the line graph. I will tell what line graph is. Line graph of G, okay, your original graph is G, okay. But why this is true? Okay, so let me give you a very hint about this, very interesting hint, okay. See, this Q transpose QS transpose is what? Now here it will be E1 E2 up to EM, then there will be vertices, right? V2. It's unlike QS. QS is basically vertices are on the rows and columns are indexed by the edges, okay. Now what will be this quantity? What will be this quantity? Its ijth entry is nothing but, so basically this, suppose this is ith row, this is jth row, so ijth entry of this is nothing but dot product of I and j, okay. So basically it tells that so suppose E1, so this is suppose EJ, let me write it EJ or EI row and EJ, yeah, okay. So EJ, this is EI and this is EJ, okay. So the dot product of this, the dot product, whatever the entries or whatever the value of this dot product, it will tell how many basically edges, so these two edges are on basically is there a common vertex between them? Because see, E1 suppose EI is this, EJ is this, okay. So the dot product of EI and EJ will tell whether these two edges has a common vertex or not, okay. If common vertex is 1, okay, then in the B part there will be at ij position it will be 1, right, okay. Otherwise 0, otherwise this will be, they are not they do not have any vertex in common, this will be right. Now the line graph is this, okay. Line graph is, so suppose line graph of this, if I have to find a line graph of this this graph, maybe this, let me put one more, okay, line graph of this graph. So whenever there are edges you put vertices, okay. So suppose this is vertex 1, vertex 2, vertex 3 and vertex 4, okay. And now if two edges are basically in the original graph, if two edges has a common vertex, okay, the corresponding vertex that you have replaced from the edges, you put edge between them. So for example here the vertices will be V1, V2, V3 and V4, right. Now you can argue, so V1 and V2 will have edge because they are common. Maybe this is again a square, okay. Very good. So V1 and V4, yes, V1 and V4, V1 and okay, so V2 and V3, V2 and V3, okay, and then V4 and V3. Okay. So basically it is again coming out to be square. Okay. So yeah, so line graph, I hope you understood. So whenever there are edges, you replaces these edges with vertices, and these two vertices will be having an edge if the corresponding edges are sharing a common sharing a vertex there. Okay, very good. So now, and what about the diagonal entries? Diagonal entries are nothing but basically it tells that so it's a dot product of an edge with itself, right? Okay, so if you take dot product of with itself, right, it will, because it at two places it will be 1 and 1, right? So it will be giving you 2, right, because there are two endpoints of it. Okay, very good. So what? So what? This tells that an eigenvalues of, by the way, this matrix L mod L and eigenvalues of QS transpose. So eigenvalues of okay, QS transpose and QS transpose, in fact the non-zero I think this we have already seen in some exercise. The non-zero eigenvalues of these and are the same. Why this is true? You please go back to your assignments or some DIY question. Okay, in fact A, B and BA have the same non-zero eigenvalues. It's very, very easy to prove. Okay, so that means what? That means what? If two graphs have the same line graph, if the two graphs have the same line graphs, okay, then they will have same basically this I would say the same basically the number of vertices has to be also same. Okay, here, so in particular if you see that for these two graphs, what will be the line graph, right? Okay, so if you draw the line graph of these two graphs, so let me again draw those graphs. Okay, so one was this and was this. Okay, so line graph is nothing but here again a triangle will come. Okay, and here it will be what? Again a triangle, right? Again a triangle. Very, very good. Very, very good. Okay, so these two graphs have the same line graph. So that means what? The eigenvalues of this signless Laplacian here for this, because the same number of vertices here, it will be same. Okay, so these graphs are cospectral with respect to signless Laplacian, but not with A and Laplacian matrix. These, one is disconnected graph, other is connected graph. Okay, so very good. Okay, now let me tell you finally another interesting matrix that we call Seidel matrix. Very, very interesting matrix. So Seidel matrix of a graph is a very, very, I would say, easy to define matrix. Suppose I will denote it by S, okay, and general element is Si. This matrix is very, very unlikely adjacency matrix. On the adjacency matrix, whenever basically vertex between vertex I and J there is an edge, we will put 1 there, otherwise 0. Here we will put -1 if vertex I and J have an edge, otherwise we will put 1, right? And on the diagonals again there will be 0. So basically let me write, so Sij equal to -1 if I and J have an edge, and of course I and J are different. Okay, I is not equal to J. Okay, I and not J not equal to, this will be equal to 1 if again I and J does not have edge, okay, and I is not equal to J, okay, and 0 otherwise. 0 otherwise. Okay, so now so for example this graph, suppose I take this graph, what will be its basically the Seidel matrix? The S will be this, right? S will be, so on diagonal there will be 0 zeros, so let me number them. So 1 2 is S, so I will put -1, 1 3 then again -1, again this will be symmetric matrix of this, but 2 3 there is no S, so I will put 1. Okay, so you see that this is very, very simple kind of. So in fact for general matrix you can actually write this matrix as S is nothing but some, I would say, J minus I minus 2A matrix. Very easy to verify. Very easy to verify. Okay. Now why we are teaching this? Okay. Now if you see that, so there is something called Seidel switching. Okay. You take some graph. Okay. You take some graph and do some kind of switching. Basically, whenever there are edges, you remove those edges, and whenever there were no edges, you put the edges. Okay. So for example, if you take suppose, let me cook some other graph. Okay, so suppose this one. Okay, suppose this one. Okay, now let us take maybe I will take yeah, I think it is enough. Okay, let me take this. Okay, very good. So now, so Seidel switching is with respect to some vertex set of a vertex. Okay, some with respect to some subset of vertex set. Okay, so suppose your U is some basically some subset of vertex set of G. Okay, so more clearly G. Okay, then what you do, okay, so whatever the edges which were in, so the suppose this is U, this is V minus U or U complement, I would say. Okay, so whatever these edges were going from this in G. Okay, so in S after switching, after and these were suppose not edges, these were suppose not the edges, so these are suppose not edges. Okay, not edges, and these are edges. Okay, edges. So what you do, okay, after switching a more clear with respect to U. Okay, the graph will be like this. Okay, so same U, and now so wherever there were dotted, you put basically the edges, and these will be now dotted. Okay, so yeah. Okay, so very good. So after this, so wherever there were edges, you remove them, and wherever there were not edges, you put S between them. Okay, and inside U and V, the story will be same. Okay, so no change at all. Okay, what we will prove that? What we will prove that after switching after basically after Seidel switching with respect to some subset of vertices U, the eigenvalues of basically eigenvalues remain same, more the eigenvalue of Seidel matrix of the Seidel matrix remains the same, or you may say the preserve. But why this is true? I mean, this is very easy to say. If you see that, suppose this is a Seidel matrix of original graph, right? Okay, now suppose you are basically having a Seidel switch with respect to U, right? So suppose this is vertex is U. Okay, and this is suppose not U. Okay, so of course, I mean, so this matrix will be something you can actually draw from. So all these are edges going from E to U comma so U comma U, that's all entries, right? And this will be the same transpose. Okay, so entries basically, so this will maybe I will just say SUV rather than, so this will be S, and this is maybe same S transpose. Okay, sorry, S transpose of this same. Okay, and here it will be everything is SU or S fully and SV. Okay, S. Very good. Now I mean, if you see that here everything will be what, +1 or -1 by the definition of Seidel matrices. Okay, and here also, and on the diagonal it will be 0. Okay, now after Seidel switching, what will happen? After Seidel switching, so whenever there were 1 here, it will be converted to -1, and whenever there were 1, it will convert it to, sorry, whenever there was -1, now it will be converted to 1. Okay, very good. Now this phenomena we can actually write as some similarity transformation. It is nothing that, suppose your resulting matrix is this after Seidel switching, okay, this resulting matrix is nothing but S times, okay, you multiply this matrix with some matrix D. I will tell you what D is, okay, and this again the D, so D is your this matrix. So basically this matrix, so 1 1 1, so 1 1 1, whenever these ones are corresponding to U, and minus 1 dot 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 minus 1 when they are connected to U complement. Okay, so this is very easy to see. So whenever you multiply with this matrix on the right hand side, so what will happen? So here actually, so these rows will be multiplied with these columns will be multiplied with plus 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 plus, okay, and these columns will be multiplied with minus minus minus. Again on the right hand side you are again multiply with the same matrix, so this will be multiplied with plus 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 plus, this will be with minus minus minus. So in this way, if you see that, so these guys will be plus, these guys will be minus, this will be minus, this will be plus, okay. So basically diagonals will remain as it is, whereas off diagonal blocks will be, I mean they will reverse the sign. So this is essentially this, but these two guys have the same eigenvalues. So S and we have already seen, right? So S and S complement have the same spectrum, okay. Okay, this proves that with respect to Seidel matrix, no graph is cospectral, except that when the graph has just one vertex. Okay, so for a given graph you can always choose a subset, okay, and with respect to switching with respect to that subset, you will generate another graph which will have the same eigenvalues, and most likely this will be non-isomorphic. Okay, so very good. So they generate basically cospectral graphs. Okay, very good. So very good. So with this I am stopping this lecture. In the next lecture we will tell a very nice technique to actually generate more basically cospectral graphs now with respect to adjacency matrix. Okay, so till then, thank you very much and see you in the next lecture.